In problem number 6, we want to compute the following. I'm going to try to, as much as possible, avoid arithmetic. So I'm going to try to be smart about it. Notice here, looks like we have a special matrix times our matrix B. This matrix looks like a permutation matrix, and we're multiplying on the left. So I know what multiplying by a permutation on the matrix on the left does, what action it does to our matrix. It actually permutes the rows. And so the product will be a matrix with entries. Well, the first row here is the unit basis vector transpose with a 1 in its third position, which is what we would call E sub 2 transpose, which means the first row here will be the third row, which is 7, 8, 9 of our original matrix. The next row will be the first, and the last row will be the second. Now, in part B, it looks like we have the same matrix, but now the inverse of it. And what we're wanting to do is figure out what happens when we multiply the matrix 7, 8, 9, 1, 2, 3, 4, 5, 6 by the inverse of the matrix that we multiplied our original matrix in part A by. Well, this just undoes the original permutation. And notice that we're trying to permute our solution from part A, which means the product is actually, by definition of inverse, exactly the matrix we started off with in part A, the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. We know that that's true because we could write this as the matrix 0, 0, 1, 1, 0, 0, 0, 1, 0 inverse times, this is actually the product of the two matrices in part A, 0, 0, 1, 1, 0, 0, 0, 1, 0 times 1, 2, 3, 4, 5, 6, 7, 8, 9. So formally we could show that this holds because we could first multiply this matrix times this, and since they're inverses it gives us the identity, times our original matrix, and we get our original matrix. Notice we didn't really have to write this out. I just wanted to show one way that we could express it. So going to part C, it looks like trying to do this product is going to be a pain because it's a 7 by 7 matrix times a 7 by 7 matrix. We could try to partition it to ease our work, but let's try to be smart instead. And if I look at these matrices, they actually have some special properties. Looks to me like both of them are Gauss transforms. Why? Because they have ones on the diagonal, zeros in most of the positions, but just one of the columns has entries below the diagonal. Here and here. Oh, interesting. The entries below the diagonal for these are related. In fact, they're negations of one another. Now, I recall that the inverse of a Gauss transform, or what undoes a Gauss transform, is another Gauss transform that has as its entries below the diagonal, the negatives of the original. So in other words, these two are inverses of one another, and the product is just the identity matrix, which is a 7 by 7 identity. Now the last question, what we need to do is fill in the boxes. And notice the action we want to perform is we want to take this 3 by 3 matrix and zero the entries in the first column below the diagonal. In other words, we want to just perform the action needed to create a upper triangular matrix. And so we first need to fill in these entries for the Gauss transform that will do this zeroing for us. Well, first thing we do is find the multipliers. To zero out the 4, we'll take 4 divided by 2 gives us a multiplier of positive 2. So the Gauss transform is going to have an entry negative 2. Negative 1 divided by 2 is, negative 2 divided by 2 is negative 1. So this entry will be positive 1. Now if we multiply this matrix times this matrix, the first row doesn't change at all. Multiplying by the transpose of the unit basis vector 1, 0, 0 doesn't change the first row at all. The second row, what we're going to be doing is taking every value in the first row, multiplying it by negative 2 and adding it to the second row. And so the first entry will be negative 2 times 2, which is negative 4, plus 4 is 0, which is what we wanted. The second entry will be negative 2 times 4 is negative 8, plus 1, negative 7. The next entry will be negative 2 times 1, which is negative 2, plus 2 is 0, and then of course plus 0, but we can ignore that. So this will be 0. And then when we want to determine the last row, what we're going to do is we're going to take the entries in the first row, multiply them by 1, multiply the second row by 0, so we can skip it, and then add it to the last row. So we'll have 1 times 2 minus 2 is 0, which we wanted. 1 times 4 plus a negative 1 is 3. And 1 times 1 plus a 3 is going to be 4. So that will be our result.